In this video, we're going to talk about data frame construction. We've already covered basic data frame construction from the basic DS modules notebook, where we constructed data frames from data structures already stored in Python. We'll do a brief review of that, but I would like to spend the bulk of this video talking about reading in data from files. So for this example, we create a few data structures, some lists, holding usernames, passwords, and creation dates. This could be, for instance, user data for a discussion board similar to our own for this class. So remember that Pandas series are essentially lists that have been labeled with an index. And a data frame is a dictionary of Pandas series. So a very natural way to construct a data frame from Python objects is to start with some lists that will basically form the columns of our data frame. And then to create a dictionary of those lists where the keys are the names of the columns and the values are the columns themselves. So we've seen this method before. The keys become the column names, and these lists become the columns. And this is a very natural way to create a data frame. It relies on this idea of the data frame as being a dictionary of data series. Alternatively, we could have a NumPy array, and since data frames are closely related to NumPy arrays, we could start out with something that's essentially already in a row column format and simply provide the labels for the columns and the index. So here the index is just a collection of nonsense words commonly used by computer scientists as temporary labels or names for variables. So we see that this table, this array, simply populated the table in row column format. The index got applied to the rows in order, and the columns got applied as labels in order as well. Of course, we can rely on this dictionary-like aspect of Pandas to not only access data, but to create new columns. So if we access a data frame at a new key, a new column name, we can assign a list-like, series-like object to be that new column. So here we add an email column by assigning a list to df email. We can likewise assign new rows, but instead of just having df brackets, which is going to try and access a new column, we would use the lock method to access a new index. And keep in mind, lock is referencing index values, not position. In this case, it so happens that the indices are an enumeration of positions, but I could even have 4 here, and in our output, the index doesn't have to be a position. This is the third row, but it has an index of 4. And then, of course, as we saw before, we can drop rows or columns, but remember, most operations on a data frame return a copy of the data frame. So if we want to make these changes stick, we either need to turn them into mutations by providing in place equals true, or we need to reassign the output of these methods to the data frame variable. One thing I want to emphasize once again is one of the major advantages that Pandas offers relative to NumPy is that in NumPy, when dealing with a NumPy array, all data access is based upon positions. And positions are often arbitrary and not meaningful. Usually, we would rather assign some kind of meaningful label for the rows and the columns to control data access. So working with this example that we've been working with of user data for a discussion board, for instance, we might, instead of having this index be an enumeration of the rows, we might want the username to be an index so we can access different users by their username. To do that, we can either set the index at data frame creation, or after a data frame is created, we can use the setIndex method to transform one of the columns into the index. So here, we construct the data frame as we did before, but specify that the index will be equal to this list of usernames. We can additionally give the index itself a list of names, which can be helpful if we expect ever to work with this index on its own or turn it into a column in the data frame. Here we just show it a little bit differently. So we start out with username as a column, but by using the setIndex method with inPlace equals true to make sure that this is a mutation, we end up with a data frame just like we did before, where the usernames index the rows. It's important to note here that the index is not a column. So usernames is not a column in the data frame. And if I try to access username, I get a key error. That's because a data frame is a dictionary of series. The index is not a series. It's not a column. It's the index, which is it's different than a column in that it's shared by all these series. All of these series inherit the index of the data frame. For example, if I select out the email series, it's also indexed by username. So username is not a column of the data series, it's the index. Sorry, it's not a column of the data frame, it's the index. We can always access the index by looking at the data frame's index attribute. To reset an index, we can call the resetIndex method. Again, with inPlace equals true, this will reset the index to be an enumeration of the rows and repopulate the old index into a data frame column. We can also set multiple columns to be the index if we wish. For instance, if we wanted both username and email to be the index, we could do that as well. Now, why is it so important to use indices and column names that take advantage of these meaningful labels? Well, it's not only for data access, where it's easier for us to simply remember who we're looking for or what properties we're looking for when accessing columns or rows, but it also actually controls the correspondence between different pandas objects when we work with them in tandem. And we'll see more of this later when we get to group bys or joins. But taking a simple example, if I have two pandas series, both indexed by the letters A, B, C, but in a different order, So series A, series B. The index actually controls how these two series will interact. For example, if I do series A plus series B, I end up with 2, 2, 2 as the result, because the value at index A in series A got added to the value at index A for series B. So the index controls interactions between pandas objects, and this can become really important and really powerful if we have, for instance, some kind of data aggregation that we've performed that we want to use to control further aggregation of another table. So this is a really powerful idea, that the names should be meaningful and should control computation. And it's one of the reasons that I emphasize throughout my discussion of pandas that we should always try and take advantage of the index and column names and make them as meaningful as possible. So with that refresher covered, let's turn our attention to reading data from files. Pandas provides a lot of methods for reading data from files. We can read JSON files, CSV files, Excel files, Python pickle files. We can even read data from HTML, whether that's stored locally or on a web server, or a database connection, like a SQL database. And we'll revisit some of these in the future when we talk maybe about data munging from web sources for HTML, or when we talk about working with SQL databases. But for now, we're going to talk about reading from CSVs. CSVs are one of the most common formats for representing tabular data, so I'd like to begin our discussion there. If we look at the Pandas documentation for read CSV, we see it has a ton of optional keywords. There is one required argument, a path to a file, or a file handle, or file buffer. So we have to provide a source of the CSV data, some file. But after that, we have a ton of keyword arguments with sensible default values that we can use to control how the file gets parsed into the data frame. And almost any time I read a CSV file into a data frame, I first inspect the file to know, for instance, is it delimited by commas, by pipes, by semicolons, by tab characters? Does it have a header? Is there a column I would like to set to the index? I look at the file and get a feeling for how the data in the file is represented. And then I look at this documentation and try and find what keywords I would like to use to help me parse the file according to the way the data is represented to construct the data frame I want. Let's see that in action. So I'm going to create a CSV file, we see it here, from our earlier example of users' information on a message board. So we have here read CSV example.csv, and we can see we have a header. The fields are separated by commas, and there's nothing obviously called index. If we simply call pandas.readCSV on this file, we'll get out a data frame that looks roughly like what we were working with before. We get each name in this first line is turned into a column heading, a column name, and then each row is read in, split up by commas, and apportioned to the columns in order. If I decide that, for instance, I want to make username the index, then I can simply add the keyword index call equals 0, column 0. And then when I read in the file, instead of having a index that is an enumeration of the rows, username gets set to be the index. How could I figure out that I could do this? By looking at the documentation. If I was wondering to myself, how can I set a column to be the index? I might just do a Control F search on this page for index, and I see here is index column. Column to use as the row labels of the data frame. If a sequence is given, a multi-index is used. So I can supply an integer or some sequence of Boolean values or integers specifying which columns I want to use as the index for this data frame. Let's look at a slightly different example of some source data. So we have the same exact data, but now this example has no header for the column names. How would we deal with a situation like this? Well, looking at the file itself, I can see this is obviously an email. This looks like what could be a username, since it's pretty similar to the email. We have a kind of random string here, which my guess is that it's a password, and then a date, which is probably the date at which the user was created. In fact, if I'm handling this data, I probably have access either to a data dictionary that tells me the format of this file, or I maybe created this file myself, and I already know what these fields are. I can tell readCSV that there's no header in my data, and that the column names I should use are these. Again, if I wanted to know what keywords are available, I would simply look at the documentation. Very close to where we found the other keyword for index column, there's a header keyword that specifies the row number to use as the column names. Since there is no column or row to use as a header, we say none. For the names, we can supply a list of column names to use. And if I had done Control F column names, it would have brought me to these keyword arguments. So by supplying the column names to use, we again end up with the same data frame as we had constructed before. Let's consider yet another example. Here, our file has a header again, but instead of being separated by commas, the fields are separated by tab characters. The separating character between fields is called a delimiter. So if we search for delimiter in the documentation, we find there's two keyword arguments, separator and delimiter. Delimiter is just an alias for separator, where we can specify what kind of character we're using to separate the fields of our table. \t is the tab character. So if I do print before \t after, I get before tab after. So we'll set our delimiter to be \t. And we can read in the data file without issue. To take this example even a little further, if we ask what are the data types of the columns that get read in, we see this date created column is of data type object, even though we saw before that we could have a date time column. In fact, if we access date created 0, we see this date is not a date time at all, but rather a string. Looking back at the readCSV documentation again, if I just search for date time, I find some keyword arguments relevant to date times, including parse dates. I can give it, for instance, a list of integers or names of columns to parse as date times. And when I do that, and I check the data types, this date created column is now a datetime has a datetime data type. And the objects contained are datetime objects, Pandas timestamps, which we'll talk about in a later lecture in this series. Read CSV is a good basis for understanding the other methods for reading in different types of files. We'll briefly go over an example of reading in JSON, since JSON is another very common file format to encounter. But since there are so many, I wanted to highlight that the Pandas documentation, which we've been making use of, is very, very useful. Not only does it contain very detailed entries for each Pandas method and data structure, but it also has very detailed user guides describing how to accomplish various tasks within Pandas. So it has an entire section about I/O tools for reading and writing files, or reading and writing data from the web or databases. I'm not, for instance, going to go over how to read and write Excel files, but if we were interested in it, we might go to this user guide and search Excel, and there's a whole section, looking at my search bar here on the right, there's a whole section where it talks all about Excel, how to deal with older Excel files as well as newer Excel files. And it gives plenty of code examples, including how to read separate sheets of an Excel file, and how to deal with various complications that may arise, parsing dates, parsing particular columns, as well as writing Excel files to disk. So Pandas is very compatible with Excel. Just to show one more example of reading data from file, our Yelp DF is constructed from a JSON blob. So at the beginning of the notebook, we read in this gzip compressed JSON blob, and we read that into our Yelp data variable. And then we pass that Yelp data variable to the Pandas data frame class to create a new data frame object. But we didn't need to separate this reading in and parsing of the JSON from the construction of the data frame. We could have constructed a data frame directly from the JSON by using the read JSON method. So if we look at the read JSON method, I want to call attention to two particular keyword arguments that are particularly important. First of all, JSON may be stored in a file as a long string or on multiple lines of the file. So there's a lines keyword for designating whether or not the file has the JSON objects broken out by line or as one long JSON string. But the most important keyword is this orient keyword argument. And the reason is that JSON is often not used to represent tables. It's often used to represent data that, in fact, can't be easily represented in a table. And I already discussed that a little bit with respect to this Yelp data. But because of that, there's no standard format for representing a table in the JSON structure. And it's possible that when we try to map the components of a JSON object into a data frame, that there will be ambiguity between what should be interpreted as a column or an index, a row, all of these things. So we need to tell pandas what the orientation of our JSON structure is with respect to the data frame. One of the most common orientations is records, where we have a list of dictionaries for our JSON object. Each dictionary is essentially a row in our data frame, and the dictionary has the keys corresponding with the column names and values for each of those column name keys. However, index or column orientations are also common. Less common is the split orientation, where we have a dictionary JSON object with an index, column names, and then data as an array. But that's also possible. In our case, let's have a look at the JSON object itself. We will cat or zcat the compressed file, and then pipe that to head in bash. And looking at this, we see that this is a records-oriented file. Each business is a dictionary, and the keys of that dictionary are the column names. So we have a list of dictionaries where the keys of each dictionary are the column names, and the values are the values for the cells in that row, column by column. So if we were reading this file in, we would want to do pandas.readJSON data yelpjson.gz orient records. Now when I try this, I get an error. And the reason is because this JSON is compressed. If we want to decompress the file as we read it in, we additionally need to tell pandas what the compression is. By default, it should be able to try and infer if the file is compressed using gzip compression or zip compression or BZ2, but for this file, it's failing to infer that. Compression. I think there's a mismatch perhaps between the version of, so I'm looking at the 24.1 documentation, and the version of pandas I'm using is 20.3. So if we are careful about that and go to the correct documentation, pandas 20.3 documentation, and then we go to IO tools, read JSON, I wanted the read JSON method. If I go to, let's see, just search for read JSON in this documentation. Here we go. No mention of compression in this documentation. So actually, I guess for the version of pandas that's installed on your machines, 20.3, the read JSON method simply cannot decompress files on the fly. So one thing this illustrates is, for the most part, very little changes often from version to version of different packages, and usually it's okay to use the documentation for the most recent version, but sometimes there are differences, and then we need to be careful. So when I was told read JSON got an unexpected keyword argument compression, I knew, since the 24.1 documentation said that keyword exists, that I must be looking at the wrong documentation. And indeed, there was a version mismatch. So what can we do? Well, first of all, we could try two different approaches. First of all, we could read or open the file with the gzip module to decompress it. And then, we could read from the file buffer, the decompressed file buffer, the JSON out of that file buffer. That still didn't work. Trailing data, lines equals true, and then my kernel died. Great. I have a little bit too much data in my memory. Not to worry, my kernel's restarted. Initial value must be string or none, not bytes. Okay, this worked earlier. I'm not sure why it's not working now. I tested this. Okay, so this is one approach. It worked earlier. It's not working now. I'm not sure why. Another approach is, if we're simply not dealing with a gzipped or compressed data file, for instance, if I unzip this, so now I have just a Yelp JSON file. I no longer have to worry about this compression issue. So orient records, lines equals true, and there's our data frame. Same as we constructed at the beginning of the notebook, but now done in one line using the read JSON method. So that concludes our discussion about data frame construction and reading in data from files to a data frame. We, again, will explore reading in data from database connections when we talk about SQL in coming weeks, and reading over the internet from HTML on websites when we talk about data munging in following weeks as well.